Hello, welcome everybody. My name is Joanna Rutkowska. This is Alexander Teroshkin. We represent Invisible Things Lab here. Invisible Things Lab is a consulting company. We focus basically on operating system security research. You can find more about us at this address. Today we're going to talk about two things. We're going to talk about Vista kernel protection and why it doesn't work. And also we're going to talk about virtualization-based malware. And you'll see what are we up to actually. Does it work okay? You hear me everybody well? Yeah? Okay. So digital signatures for kernel drivers in Vista. As you all know, Vista has a requirement that all the drivers needs to be signed and even administrator cannot load them. These are the quotes from the official Microsoft documents that explain the reasons that Microsoft decided to implement it. Because as we know, it's a very controversial feature because many people complained that why they actually need to buy a certificate if it's like their own computer. If it's their own computer, they should be able to load whatever they want. And Microsoft doesn't allow them to do that. So Microsoft replies in such a way that they believe digital signatures are an important way of kernel software, are an important way to ensure security of computer systems, and also that they increase safety and stability. Even users with administrator privileges cannot load unsigned code on x64-bit systems. Last year here in Vegas, I presented Pagefall attack, which just relied on some design problem in Windows that allowed a user mod process to actually load unsigned code into Vista. That has been fixed a couple of months later in Vista RC2 by Microsoft changing a little bit the API used for accessing row sectors. Right now, it's not possible to, at least on Vista 64, it's not possible to open row disk access to a volume without first locking the volume. And in order to lock the volume cannot have an open file. So obviously we cannot open row access to a volume which contains page file because page file is opened. So for today we came up with some other attacks. Well, the attacks we're going to present are pretty obvious from the philosophical point of view. It's just Vista, like all other general purpose operating systems, like Linux, FreeBSD, it's a huge monolithic kernel design. There are like hundreds of, or thousands, or maybe tens of thousands third-party drivers available that are signed and then could be loaded into Vista without any problem. Many of them are poorly written. Now Alex will tell you some more. We'll present you two examples of two bugs that we found in some commonly used drivers. Yeah.
As you know, many drivers have interfaces for calling some of the kernel mode code from user mode. This driver, which presented on the slide, is included in the ATI Catalyst package. And it has a few interfaces for reading and writing kernel mode memory from user mode. Actually, as you of course know, only administrators can install drivers. So only administrator can use this interface if there was no such driver loaded before the attack. So if you consider old days when XP was running, for example, there was no such problem, no such security problem, because administrator could really install any driver. And if a driver developer has to implement some features which can't be used by operating system interfaces, it was okay to implement such interfaces using driver agents. But for now, when administrator cannot install unsigned code, it became a security problem, because if an attacker can find some vulnerable driver which was signed by a valid certificate, it can install it, of course, because it's signed, and then abuse its interfaces to do some attacks. For example, this one can be used to overwrite any byte of kernel memory from administrator account, of course. So, for example, we may overwrite the variable which controls the behavior of Vista, and it enables or disables the feature of driver signature enforcement. This is the code that actually validates the image of the driver, and first it tests the value of GCI enabled variable, which can be easily overwritten by the exploit which used, for example, ATI driver. Here's the certificate of this driver. You see that it is valid, and if attacker has the binary of such a vulnerable driver, it may easily install it. Consider another type of bugs. These bugs are not used for reading or writing memory from kernel, but, for example, this driver, which was included in NVIDIA Enforce driver package, actually in Entune software, is able to read and write MSR registers, machine-specific registers, on the command which was passed from user mode. Administrator can install this driver because it's signed, and user interfaces like this one, using ordinary device user control routines. And you see there is no any checks for the number of the machine-specific register which is being read or written. So an attacker can specify, for example, L* register, and it may overwrite it with any value, and we have a shellcode for it. Look at the shellcode. We may set the L* value pointing to this shellcode which is located in user mode and execute it. First thing that this shellcode will do is to restore the original value of L* register. And after this, it will be safe to perform any syscall instructions from our processors, of course. But we already have our shellcode executed with kernel mode privileges. So we may do here basically anything. And what we do here is we allocate a memory for the executable code, copy the driver code there, and run its entry point. I assume this driver image was a portable executable image. So we may load and run virtually any driver, even if it is unsigned, of course. This is the slight update of the previous shellcode. It allocates a kernel mode stack for it. This is because a few Vista functions check for the stack, which is currently used by the CPU. And for example, we cannot create any kernel mode threads without allocating kernel mode stack for the functions. So this shellcode is actually used in an exploit which can load any unsigned code in Vista.
Okay, just one more clarification for those people who are actually less technical. So the whole problem, for example, in this driver is basically, well, this is a routine which is called in a response to a IOCTL sent to a driver from a user mode code. Normally drivers exposes lots of interfaces like this. The problem here is that basically this driver does not do the proper check, because here a user mode process can simply ask a driver to do a write to MSR register, an arbitrary MSR register. The driver should not allow for that. This is the problem here. Okay, so I'm sorry, I'm speeding up because we have like 120 slides for today. So I try to... Sorry, we got a lot of stuff actually. A quick consideration: you might be thinking, okay, if we have like not a buggy driver, like we don't have a buggy, if we don't have a hardware for which like NVIDIA or whatever those bugs were, then maybe we shouldn't be not afraid. This is not a problem. This is not a case just because the hardware actually, the driver actually does not need to be present on the target system. The attacker can actually bundle the driver to its rootkit pack, and just the first thing he or she will do is just load the buggy driver, which Vista will allow to do because the driver is signed and there is no reason not to allow for it to load, and then it will exploit the driver back, and then will load any other unsigned code like rootkit.com. The nice thing about this shellcode, which Alex also didn't mention, was that it allows us to load any pe.sys driver unsigned, and the loading does not involve official API by the operating system, which is used for loading drivers. So even if we have host IPS that is supposed to filter our driver or control driver loading, this all happens beside it. So it doesn't matter actually whether we exploit a problem in a popular driver or not popular driver. This is actually pretty popular, but we could find some exotic driver in some stupid keyboard, and always we can bring it to the target system and load it and exploit it. Okay, imagine an ideal world when all the developers for Vista drivers will be writing bug-free code. Still, we can get around this because it's possible to. Because the Microsoft does not require people to submit drivers for signing, all I have to do as a developer is to buy a certificate for signing. And I actually spent 2 hours doing that. It costed me $250. I just went to Global Sign. I just applied for a certificate. I put my official company name, Invisible Things Lab. I put my official name. They asked me to send this form. I need to sign it. I need to provide the company registration form, plus my ID, and send them by fax. And after 2 hours, they send me back my certificate. We have it right now. Invisible Things Lab. You see that we have a private key. We can sign whatever code we want. Obviously, it wouldn't be wise for anybody to sign a malicious code. However, nobody can prove me that I can write some tool for kernel which would be doing something. I don't know, would be a process monitor, for example. And I can make unintentionally a subtle bug there, like a buffer overflow, whatever. And then I can put this driver on my website and make it public. But nobody will know about the driver. And then I can actually use this driver, bundle it to my rootkit, and again, load the driver first, exploit the bug, load the rootkit. Even if somebody finds out that actually the rootkit uses a driver signed by Invisible Things Lab, nobody can actually prove me that the bug I did was intentional, because we all know that software developers do a lot of bugs. However, we don't have to do this right now because we have dozens of bugs in those drivers. Alex finds them in his spare time, and it's really easy. I'm going to skip some of the slides. This presentation will be available for download. I will give you a link later so you can walk through all the slides later. One of the solutions, probably the most elegant solution to this problem, the problem of securing a kernel of the operating system, so the problem of making sure the integrity of the operating system, the solution is to use a microkernel-based operating system. For example, if you look at Minix 3, it's an operating system which keeps all the drivers in user mode in their own address spaces. One nice step made by Microsoft is something which is called UMDF, User Mode Driver Framework, which allows to keep some of the drivers, some PDAs drivers, USB drivers, in user mode processes as well. However, this is very, very immature solution right now. Immature in the sense of that there are just 3 classes of drivers you can put there maybe, and all other drivers like keyboard, graphics card drivers, network drivers, everything else should be real drivers in kernel. The message of this part is basically that we don't believe it's possible to create an effective kernel protection in a general purpose operating system based on monolithic kernel design. We think that, if Microsoft did at least that, if they establish a third-party driver verification authority, would be required for all developers always to send a driver then in a form of source code, the best, and only after they evaluate it, they give a certificate, that would increase the bar a little bit. It would rise the bar a little bit, sorry, but it will not solve a problem. Okay, second part of this presentation. Please make distinction between the first part and the second part. Last year, I also gave like 2-part presentation. People were like confusing Bluepill with Pageful Attack. So these were all about how to load stuff into Vista kernel, which officially does not allow to load stuff which is unsigned. So once we have this ability, let's think about how we can subvert it. Our original idea was to also talk about type 2 and its subversions at this lecture, but because we already have 120 slides, I decided to skip this part. So we will go directly to virtualization-based malware. We're going to do a little intro, 5 minutes, and then we will talk about, we spent like half an hour talking about detection. And then we will talk about nested scenarios and why they are actually important. Yeah, that's very easy. We have software and hardware virtualization. Software basically is what is currently mostly used. Hardware is what is actually coming. And Bluepill, the malware I presented last year, made use of hardware virtualization. The nice thing about hardware virtualization is that it allows to create very thin hypervisors in a very easy way, at least at the beginning. I make a distinction between full VMMs and thin hypervisors. Full VMMs are interested in emulating or virtualizing the whole system together with all the I/O, with all the devices. However, the thin hypervisors are interested only in controlling the system in a stealthy way. Original Bluepill was presented here last year by me. Also, Dino Daizovi presented Vitriol, which was, while Bluepill was implementation on AMD SVM, Dino's rootkit was implementation on VTX, on macOS, I think. In May 2007, after I started the company, we decided to redesign and write from scratch the new Bluepill, which implements many new features and also has a completely new design. Design in terms of like it uses HVM layer similar to Zen, so it allows, hopefully it will allow to easy port it to VTX architecture. Currently we only port it to SVM. The idea of Bluepill, probably everybody knows, is just we have the operating system running. Attacker somehow gets his code into the system. The code is executed. The code creates a virtual machine and then moves the native operating system into a virtual machine. Itself becomes a hypervisor and resumes the guest. And the assumption is that the guest cannot actually realize that actually it has just been moved to the virtual machine. The whole process takes like 1 millisecond on the fly. So SVM is just a set of instructions, like a couple of more instructions added to ISA of PC architecture. In order to use them, we need to set SVME bit in ether register. And this is the most important probably thing when we consider SVM detection methods, because all of them will be actually trying to exploit this fact that SVME is set and that a malicious hypervisor is trying to hide this fact. Just like 10 days ago, AMD released another a new specific update of its manual, where they released a new specification of SVM. It has an additional layer of security for enabling SVM mode, which you see. Okay, basically it's like we have a special register, like a password register, where we can put a value, and then this value is like cannot be read anymore. And then if anybody wants to set the SVME bit in ether register to enable SVM, he or she needs to know the password first. However, one more solution that has been added over the last months was more and more computers have an option in BIOS that allows you to disable virtualization. For example, yesterday we had a training and we found out that actually the machines that were delivered for the training had actually virtualization disabled in BIOS. However, we don't believe that virtualization disabling is a proper way to protect against like Bluepill-like threats. Just because virtualization has lots of legitimate usages, it's a great technology. For example, Virtual PC 2007 already uses hardware virtualization extensions. And in the next year, next 2 years, we'll probably see more and more applications making use of hardware virtualization. So basically, disabling virtualization is basically saying, let's disable your network card so you'll be avoiding network attacks. This is how SVM is normally used. It's just the VMrun instruction is the heart of SVM model. From this slide on, I focus on AMD SVM architecture. There's mapping almost one-to-one between VTX and SVM, but we focus on SVM just because we are familiar with this, and we are familiar with this just because we have a couple of machines to do the tests on. So normally we just fill a VMCB block, which describes the guest and what we want to intercept in the guest. VMrun creates for us a hardware virtual machine and starts executing it until an intercept occurs inside a guest. And then the execution is coming back up the instruction after the VMrun. This is how the Bluepill IDEA. This is the presentation of Bluepill IDEA. So what we do is just at some point of time, we just initialize it. So basically, we've somehow managed to get our code executed by the native operating system. Our code just enables SVM, prepares VMCB in such a way that this VMCB actually duplicates the state of the currently running operating system, and then executes VMrun. However, RIP, the instruction pointer register, we make it point to write instruction from this function. Then we call VMrun instruction. We execute VMrun instruction, which basically creates a virtual machine, starts executing from IP address, which is the right address. So basically, it starts executing all the instructions after our call to Bluepill inside the virtual machine. So basically, we resume the guest. However, the guest is now executing inside the virtual machine. And we here becoming a hypervisor. Nothing couldn't be actually simpler than this. The whole point is, this all happens on the fly. There is no reason to reboot the system. We don't have to modify anything inside MBR or whatever. We do not virtualize any hardware. We are a very thin hypervisor. We allow all the I/O to go through. So there should be no performance impact. If you have your favorite 3D graphics card, it still be supported after you load Bluepill. Okay, detection. Before we move on to detection, let's do a very important distinction. After I presented Bluepill here last year, there were a couple of people releasing papers, about maybe almost 10 different papers. Everybody was Bluepill detection. However, all they did actually was AVMM detection or SVM detection. So please distinguish between detecting the presence of a VMM, a virtualization or SVM mode, from detecting the actual virtualized malware. This will probably become more evident for you when we go to the nested virtualization at the end of the presentation. Just keep in mind this distinction for now. Okay, I'm going to exaggerate just to illustrate the difference for you. It's like the SVM detection, if we say that it's equal to Bluepill detection, it's almost like if we said that we can detect a botnet agent by looking at the executable, and if the executable actually makes use of a network, then it's a botnet agent, right? This is a little bit exaggeration, but hopefully you get the point, and we'll get to this later when we talk about nested stuff. So let's focus first on this one, because it's still interesting. Well, of course, we have timing analysis. We have lots of... actually, instead of just talking about this, I'll just move on there. So let's use timing analysis first. As I said, because we need to set this SVM bit in if register to enable virtualization. So basically, Bluepill probably would be interested in actually cheating about this bit being set, just because if it did not, then we would just look at the if register and see, SVM bit is set. This is suspicious. So probably would be interested in cheating this bit. So the simple way of detection is just, well, not surprisingly, there's a read-MSR-FR instruction, which is used to actually get the value of IFER register. So not surprisingly, the read-MSR-IFER register on a clean system takes like about 100 cycles. However, on a system with the Blue Pill installed, it takes like, for example, 2,000 cycles, or in case of our Blue Pill, like 10,000 cycles, because our Blue Pill is pretty complicated. By the way, lots of people are saying that actually you can use CPU. So all the methods are using read-MSR-IFER because people know that if there is a like Blue Pill or something, they will be intercepting read-MSR-IFER. However, lots of people suggest that CPU ID instruction is something that is always intercepted. This is not true. We actually do not intercept CPU ID instruction, and we cannot do this perfectly. So well, we can intercept CPU ID, but we don't have to do that. The only thing right now we have to do, if you want to cheat about SVME, is to intercept read-MSR-IFER, not CPU ID. If somebody tells you that CPU ID must be intercepted, then probably they have experience with VTX only. I'm sorry, we're going to do questions later because we're really speeding now. So. This is just some examples. As I said, clear 100, Blue Pill like about 10,000. So how can we measure time? Well, we can obviously use a timestamp counter using read-TSC instruction, which is the best for measuring like execution time of an instruction because it has a great resolution. We can maybe use HPET timers as well, but which also have very good resolution, but they are still local. We can use real-time clock, which is also a local device. However, it has a very poor resolution, and eventually we can use NTP protocol to get trusted time, because not surprisingly, all the first three can be, I'm not saying trivially, but relatively easy cheated. For example, HPET timer, which generates interrupt, is quite easy to actually cheat because we can basically intercept and interrupt, which is a standard operation in SVM. So let's start with read-TSC cheating. Last year when I was giving this presentation, I told you that you can actually use TSC offset. This is what documentation says actually, and even today we saw a presentation on Virtual 2008 server, and they said that they could use TSC offset maybe for virtualization. However, this doesn't work well just because the variation, like sometimes read-MSR-FR would take 8,000 cycles, sometimes 10,000 cycles on a Blue Pill machine. So we don't really know what's the good value for TSC offset. So basically, it's not really precise. So we can, if we just decided to put like minus 10,000 in 9,000 in TSC offset, sometimes we would be getting a negative timing for an instruction, which would be pretty suspicious. So that's why we came up with this simple, funny method of cheating with TSC, which is based on some anti-debugging techniques. Quite popular in Russia, I guess. So it simply works by intercepting read-TSC. After we intercept read-TSC, let's say that the read-TSC at the top of the screen is the first read-TSC ever. So after we intercept read-TSC, we set a tracing flag and we start tracing the next 100 instruction of the guest. And then for every instruction, we increase some variable, emulated cycles variable, with some number which is the expected latency of this instruction, which we take from AMD optimization guide. When we see another read-TSC instruction within like this range of like 100 tracing instruction that we trace, then we actually return here TSC offset as seen by the first instruction plus the emulated cycles. If like within the next 100 instructions there is no read-TSC, we stop tracing so not to increase any performance impact. Obviously, some of you may say, of course, this will not work on modern processors because modern processors have parallel processing. They can execute several instructions in parallel, reschedule and whatever. So it's not like that if we have 20 instructions, one after each other, then the cumulative time of execution would be just the sum of all the latencies. However, we can modify it in such a way that we'll be just recording opcode of each instruction, those like 100 instruction, whatever, and then we'll have like a function of all those recorded instructions that will be trying to determine how much it takes. Now, if there would be a significant difference, there would be some configuration of instructions to give like a significant differences in execution, like will exploit this parallelism of processor that detector would be able to detect, then we can use the same algorithm to create this function. Of course, we did not implement it. Actually, we didn't even implement this f function, which would be returned the expected latency of the instruction. We just put like 7 for every instruction. It works pretty well. Just the fact is, the variation of a execution time of like 100 instruction, whatever, we have a variation even on a clean system. It's too subtle for the detector to notice. Well, the difference, like 100 and 10,000, is not subtle. It can be pretty easy notice. But like 50 versus 70 cycles, this is not really detectable, like noticeable by the detector. So this is like proof of concept we can use to cheat it. That's what I just said. Obviously, this is still not enough because somebody can use this trusted time source, for example, using NTP server. So you just ask NTP server, and then you execute read MSR a big number of times. Obviously, big number because the time from the network is like maybe 10 millisecond resolution at best. So you need to execute like hundreds of thousands of those instructions to actually notice any difference. So obviously, Bluepill cannot generically intercept all possible external time sources. Obviously, somebody can say, well, we can intercept incoming packets, NTP packets, and modify them, but this is really implementation specific. Somebody might use encrypted NTP, and we will not be able to do that. That's why we came out with this funny chicken strategy to actually get around this problem. It's basically about, it's just, if we detect that somebody generates too many intercepts in a too small period of time, then we need to sleep for a few milliseconds. Of course, we cannot sleep really. Instead of sleeping, we are just uninstalling for like 10 milliseconds. And we allow this detector to execute those read-MSR if or then, which execute natively. Yeah, we have several challenges here to implement this, actually. This sounds very easy, but please remember that there is a Bluepill hypervisor, there is a running operating system inside a virtual machine controlled by this running hypervisor, and suddenly you want to uninstall. So we now need to move this running virtual machine inside this running virtual machine, move it out from the virtual machine back to the native hardware, all on the fly. Alex will tell you how we actually coded this. Actually, Alex coded this. This is actually how we detect the timing attack. It's just that we have a shifting register, let's say 100 slots. Every time the intercept occurs, like read MSR ether, for example, we put in our Bluepill handler, we put into the register the TSC offset when this intercept occurred. So we keep track of, we keep a timestamp of each of them. And then every time we check whether the T0 minus T1, Tn, the first with the last, is not smaller than some time threshold. If it is, then it's a signal to uninstall, and this is what Alex will tell you how actually was coded.
In order to uninstall correctly, Bluepill should restore the state of the guest, or which was on last VM exit. So it should generate a buffer of the executable code, which will restore all the general purpose registers to their values, which were set by guest on last VM exit, and of course restore all the system registers, like it should reload CR3 register to point to the original guest page tables. But in case of Blue Chicken strategy, BluePill does not have to resume guest right after the VM exit to the original state of the guest on this VM exit. Rather, it should set the RIP pointer to the special routine which will install so-called time bomb, which will execute in a few milliseconds, for example, and then install BluePill again. So to do that, we have to restore all the state of the guest except the RIP and maybe a few more registers, and then call our routine on the resuming of the guest first. So after that, we set up a special DPC, which will execute in a defined after the defined time will pass, and that routine will install BluePill back. And to do this, we just run another trampoline code. Trampoline code which will restore all the general purpose registers of the guest. So there will be no difference for the guest state between the last interception of the BluePill and after we call the trampoline code. So all the state will be the same.
By the way, yesterday during the training, we had like 50 beta testers for this technology. So it turned out there's some weird race condition there, and from time to time we get the blue screens here. So it's not really like fully implemented right now, but it works usually. It's just very tricky to implement. It just sounds like so easy, but it's actually pretty tricky. You might think that right now, well, this chicken strategy is like has a sexy name, but it's actually pretty not really useful because, well, a detector might just knowing that we do this, and please remember the whole idea about BluePill is that the opponent knows how BluePill works, exactly, knows the BluePill code. So somebody might say, so we can write a detector that would be like execute a thread, and this thread would be like executing this readMSR ether in the loop to make sure that BluePill will be like always unloaded. However, please note that a detector would be consuming your CPU time to do this. So in case let's say if you want to make sure that BluePill is 90% unloaded in 90% of time, then the detector would have to use 90% of your CPU to actually generate those readMSR ether instructions, which is a pretty bad deal. Another strategy for the detector here could be to just execute like those readMSR ether instructions, like 1 million of them, and then knowing that this should force BluePill to unload, load itself. So the detector would now would use exactly the same idea as BluePill. So detector would do exactly the same as BluePill normally does. It would install itself on the fly, move the operating system on the fly into virtual machine, becomes a hypervisor. So we would get rid of the BluePill, but now we would have a detector in the hypervisor, which again is not that good because now the question is, so let's say I want to run Virtual PC 2007 because I just want to use some virtual appliance or do some stuff in virtual machine. I run virtual machines all the time on my desktop. So what would be the interface to tell this detector BluePill to allow Virtual PC to load? Well, there would be some interface probably. So maybe the same interface could be used by BluePill to actually ask this detector to allow it to get in. One more attack. We just learned about it like 2-3 weeks ago. It was presented by Edgar Barbosa at Syscon conference in July. So this month. Actually, Edgar worked with us when we were in Kassel, was on my team. So what he presented is, instead of using some kind of time source to time profile the read MSR ether, let's use another core of the CPU, which is a counter. So we have 2 threads. Detector needs to set 2 threads. It needs to make sure that each of those threads run on a separate core, and then they need to synchronize the start of the execution of the 2 threads. And now what one thread would do is would just do a for loop, just a stupid loop, which would be looping until some variable gets true, is set to 1, and while looping will be increasing some variable, a counter variable. While at the same time, the second thread running on the other car will just execute readMSR ether. And the problem here is that even the blue pill will get control eventually. It would be too late. The blue pill gets control only here because the first 1,000, 2,000 cycles is actually spent by the processor on doing the VM exit, on transitioning from the guest to the hypervisor. So during this time, the counter will count 2,000 maybe, while if there was no blue pill here, the counter would count 100. So what do you think would be a method to defeat it? Does anybody know an idea? Well, I'm asking just because we haven't found a generic method to defeat it right now. This is a beautiful attack, actually. It's the simplest attack of all that we're going to talk about. Of course, we can defeat it if it was if we know the detector, we can just find the counter variable and reset it or whatever. But the generic way, we haven't found a way. Well, we have been thinking only 2 weeks on this, but still, it's pretty tough. Obviously, it requires dual-core system, but today every CPUs are dual-core. So congratulations to Edgar. But still, don't lose fight. It doesn't mean that we actually solve the problem. Well, obviously here it's a... Actually, I didn't put the slide here. Okay, yeah, here are some considerations because we came up with several methods to detect it. One method could be, for example, to detect that somebody is trying to schedule thread executions on 2 different cars, and maybe if that happens, just use the blue chicken strategy. However, this is not the case because the detector could be improved in such a way that it creates, let's say, 100 threads. If we create 100 threads, and do not ask operating system to put them on a specific core. We just create 100 threads. So then there is a great probability that more or less 50 of them will get into core 1, another 50 to core 2. So all we need to do is just look at all the threads we got and just choose those that, choose one which is on one core, the other one which is on the other core. Also, we were thinking about marking pages that might contain readMSR ether, and if this and using kind of a shadow paging approach. However, here also is a problem because the readMSR ether of this thread can be put on the edge of the page, and once we realize that this page is going to be executed, it's too late already. Alex has some weird idea how to do this, but it's really too crazy. So currently, we don't have a good way to defeat this attack. However, let's stay at the subject of detecting SVM. This is all about detecting the virtualization node. One particular popular method for detecting SVM that was described by several people was TLB profiling. You see, Peter Ferry wrote a paper, Tal Garfinkel and Kate Adams, and one more person wrote a paper that they presented just a few months ago at HotOS. And also Kate Adams wrote a blog post, a blue pill detection in 2 easy steps, again based on TLB profiling. We wanted to do a little case study on this because, to our surprise, most of those people probably never implemented those TLB profilers because they missed some fundamental things about TLB, at least on AMD systems. So this is just to show you that some of the methods that sometimes look very simple actually turns out not to be that simple. Even though still we will show you actually a working TLB profiler, but it will be much, much more complicated. So TLB, you probably all know what is TLB. It's just a look-aside buffer which caches virtual address to physical address translations. Obviously, it contains much more, a little bit more than just VA and PA more precisely virtual frame number and physical frame number. It also contains some control bits, controls some protection bits. Yeah, that's pretty much it. So basically the idea is that if the processor wants to access a virtual address, it first checks the TLB. If it's not found in the TLB, then it needs to go and search for the mapping in page tables. If not, it takes like one cycle to get the address from TLB. If we go to page tables, it takes like maybe 50 cycles. Just like a tremendous performance impact. That's actually how TLB entry looks like. This is what I just said, VPN, PFN, some control bits. This is the idea of the attack. Fill TLB with some known pattern. Then use, let's say, readMSR IFER instruction. Again, readMSR IFER, not CPU ID. And then check whether our mappings are still in the TLB. Because obviously we expect that readMSR IFER that will cause VM exit, the virtual machine will at least use several of those entries. Well, because virtual machine actually, the hypervisor actually will accesses some pages of memory. It accesses the pages on which it executes and some data pages as well, pages. So we expect that some of the pages will be, some of the mappings in the TLB will be lost. This is the statistics for TLB buffer in AMD, Athlon, and I think Athlon only processors. 32 entries for 4K pages, 8 for 2M, and 512 4K pages level 2. We're going to talk about level 2 in a moment. This is the simple idea. That doesn't work. We allocate 32 because let's say we focus on this 4K page translations. So we allocate 32 4K pages. Then we actually access all those, let's say first byte 0 from all these pages to make sure that this will put the translations in the TLB. Now we do one more test. We actually, after we make sure that the entry is in a TLB, we actually use, let's say, read TSC to find out how much time it actually takes now to access this entry. So normally we expect this one would take like maybe 100 cycles, and this one should take like 1 cycles maybe just because the mapping is already in the TLB. So we save this in taccess1 table. And then we execute readMSR IFER that we expect to cause VM exit. And then we loop again through all our entries. We try again to access our pages. And obviously we measure the time here. And obviously if there is nothing in the system, then taccess2 should be equal to taccess1 for all i's from 0 to 32. So we implemented this. And actually we got this funny result, which shows that the blue bar is the taccess1, the purple bar is the taccess2. This is strange, because this shows that TLB actually didn't work here. So let's try to run this loop, this checking loop, backwards. So at least we find out maybe the TLB is actually smaller. And indeed, we ran it backwards, and it turns out that for the first 16, they are actually cached in the TLB. So we might think, so AMD is cheating about statistics. But that's actually not the case. Because if we look at this code, so we realize that actually this access time is not only time spent by the processor on translating the address, but also on actually fetching the actual data from the page. And again, here we have actually tmap plus taccess. However, we have data cache, like L1 data cache in every processor. The size of L1 data cache in those AMD processors we tested on is like 64 kilobytes. So we have like 32 bytes to actually cache. So what? Our L1 data cache is not capable of caching 32 bytes? Because if it was capable, then we shouldn't see any differences, because this and this would take the same time, because the fetching time of the data from L1 data cache would take the same amount of time. But it doesn't. So we have a suspicious L1 data cache is not 64 kilobytes, maybe it's just what, 16 bytes? However, the answer is actually in this line, that actually the L1 data cache on AMD and many other processors is actually not fully associative. It's only two-way associative. Associative. I get problems with this word. So even though we have 1,024 lines of cache, each line can cache 64 bytes, this actually doesn't mean that we can cache 1,024 random numbers. Because it's two-way associative cache, which means there are two ways, and each way has now 512 sets. And now if you want to cache this physical address, which is the physical address of this page byte we want to fetch, the processor divides this address in three fields. The offset field is not the offset field of the page field, it's just an offset field inside this cache line, which is 64 bytes. So 64 bytes, which is 6-bit long. And then we have index field, which is used to actually choose the actual set. And now the processor can cache data with this physical address only in a set which is equal to index. Which means that if we have two addresses, if we have three data, and they have three physical addresses, and those three physical addresses have actually the same index value, which is pretty common if we allocate like 32 pages one next to each other, then only two of them can be cached. All the others will be discarded, because there are only two places to cache it. Obviously, this is how to speed things up, because if now the processor tries to fetch a data from cache, it just looks at the index field, it just looks at the appropriate set, and just has two possibilities to check. So it just has to compare tag with 1 and 2 instead of 1024, which is a pretty good speed up. This is the reason why we actually cannot cache our 32 bytes in a L1 data cache. However, we can overcome this problem, because if you look at our virtual address, because we operate on virtual addresses in our detector, it has an offset field. An offset field, while we don't really control VPN, because it's what we get allocated, we can easily control the offset field by reading byte X instead of byte 0 from the page. Actually, parts of it is actually directly translated into the first 9 bits of the index field. So we can actually somehow control the index field in our test bytes. That we can control it in such a way that we will spread them evenly across those sets, so there will be not 3 bytes in any one set. So we make sure that all the test bytes will be cached in L1 data. This way we eliminate the difference of access time to fetch the data time. And this is after I implemented this. This is on a clean system. You see we actually see 21 here. The 21 here is 21 cycles. It's actually because I use read TSC, then I do the access, and then I use another read TSC, which means that this time actually contains the time of execution of read TSC instruction. Normally it would be like 1, so we need to scale it to 1. It's not important. Important thing is all those bars are equal, TXS1 and TXS2. Now it works as we expected it to work. One of them is 3 cycles higher, and this is because we use some local variables, and we actually use some stack in the for loop. They are all located on one page, so one page actually gets replaced by those local variables we access in the for loop. And now this is what we get if we run it on a system where we install the hypervisor. As you see, this is actually example for Bluepill. We get you see that it actually used 6 pages to actually handle read MSR ether access. So you see, actually, TLB profiling can be implemented correctly. However, the amount of code and the complexity of this detector is significantly higher than the simple approach that many people wrote about. Now consider that we implement this in hypervisor. It's like not really good approach. Still, it uses it uses read TSC to get the timing. We know that we can sometimes cheat read TSC. Of course, we didn't implement cheating read TSC for this attack, but somehow we feel that we can cheat it. So we can use another TLB profiling method, which was proposed by Kate Adams, also this month, which is that simple. Well, this is actually a screenshot from his blog. This is what I translated it into a human-readable form. By the way, in the morning, I saw a presentation about VM detection, and I actually presented the same method. I actually didn't mention it was actually described by Kate Adams, which was pretty strange for me. So here's the idea. We allocate n pages. Let's say 32 pages. Like the n is the number of TLB slots, the maximum number of TLB slots. Let's say it's 32. And we allocate one more page. I call it page 22. And now we've set all those 32 pages with the pattern 1-1 and the page 2-2 with the pattern 2-2. And now we access the first bytes of all those pages just to put them into TLB. And now we do the funny trick. We modify the PTEs for all those pages in such a way that actually this virtual address will now point to the physical address of page 22. And now we call readMSR ether. And now what we do is that we actually try to access all those pages again, read the byte from this page. And if we actually at least once get a byte 22, that means that the processor actually didn't find the mapping for this VA to PA mapping and actually used the page tables, so actually used the remapping that we set in PTE. So this means that actually one of the entry was replaced, at least one of the entry. If there was nothing, if this didn't use any TLB entry, then all the pages, even though we change PTE, our processor will use TLB to access all the pages. This is a very nice attack, actually, because it doesn't use any timing. It just uses the functionality. So it's actually nice. The problem is it doesn't work, actually. This is what I said. The problem is that because we don't have one TLB for 4K pages, we actually have two levels TLB. One is 32. The other, as you saw on the slide before, is actually 512. Well, not a problem, you might say. So let's set n to be 32 plus 512 to make sure that we actually will put mappings into all those entries. Right? This doesn't work either. Because TLB level 2 is also not fully associative. It's only 4-way associative. Again, we learn it by executing CPU ID instruction. That means that in order to fill the whole TLB level 2 for 4K pages, we would have to fill all. For each set, we need to fill all 4 ways. To do this, this time it's not physical address, this time it's a virtual address. So in order to do that, we need to specifically allocate those 32 plus 512 pages in such a way that we control index, that we have all indexes from 0 to 127, each time 4 times to fill all those entries. If we don't do this way, we always miss at least one entry, and we cannot have a guarantee that a hypervisor will not use actually this entry. This is actually more complex than L1 data cache collision avoidance, as I implemented in TLB Profiler, because here we need to use specific virtual addresses. Unfortunately, there is no API function to call to ask Vista to allocate page in kernel mode, not in user mode, at specific virtual address. So the way to do this would be allocate much more pages and choose the one which we want to use, which is actually probably would be quite time consuming. And again, we have a very complex detector. Again, the idea very simple. Everybody thinks it's simple. Turns out to be quite complex. But still, it can be done probably. How we could approach defeating this? We believe this could be defeated using shadow page tables, or nested page tables. I'm going to talk about this in a moment. Basically, shadow page tables would allow us to find out that the guest modifies its PTE. So if you find out that guest modifies 544 PTEs, that will be suspicious, and we use blue chicken strategy to uninstall for a moment. We didn't implement it, of course, in our current Bluepill prototype. VMM detection, just to summarize this all was about virtualization mode detection, detecting a VMM, not detecting malware. Let's move on to detecting virtualization-based malware explicitly. So what's so special actually about Bluepill? It's not really about virtualization, even though it's really a pretty sexy term these days. It's all about something different. Did I tell you we finish at 7 p.m.? Nah, I'm just kidding. So obviously we have like type 1, type 2 hooking, which is like hooking code, hooking data. The point is all the rootkits I'm aware of, besides Vitriol, they hook something, and Bluepill, they hook something, they introduce some modifications into system, hook some function pointers, hook some code. So we can always actually find them if we had, at least theoretically, if we imagine having an ideal system integrity monitor, let's say written by Microsoft, who has full access to source code. We can theoretically imagine writing an integrity detector that would check all the system, that the code is not modified. That's actually pretty easy. And then all the function pointers are not modified. For example, all the NDIS pointers, etc. Still, it wouldn't detect Bluepill just because Bluepill doesn't hook anything. It just sits beside the operating system, just looks at it and controls it, but doesn't modify any bytes. So we cannot detect it really by integrity monitoring. However, if we look at the approach that the antivirus people actually take these days, it's not ensuring the goodness, it's actually enumerating badness, which means that they actually they would like to scan memory and look for something that looks suspicious. It's actually pretty challenging because even if you can scan a memory, obviously you can find Bluepill code if we didn't use memory hiding. So let's say you find this Bluepill code. It's actually pretty easy using a heuristic approach to find out that this code actually looks like a hypervisor. However, now we believe it's very challenging to find out that this hypervisor actually looks like a malicious hypervisor. So again, it's a problem distinguishing between a hypervisor versus a malicious hypervisor. But anyway, let's talk about memory hiding. Okay, this is Alex will probably spend the next 30 seconds on detailing this thing.
It's a good idea to Bluepill to have a private page tables to use, because if it will share the same page tables with the guest, then guest will be able to modify those pages of the Bluepill code and so on. So Bluepill has to build completely different page tables, fill them with physical addresses of the Bluepill's code and data, and then execute. It probably also can remove the mappings of these pages from the guest page tables, so to that any memory scanner code which will be run in guest will not notice any Bluepill code in its memory. Actually, this approach can be defeated by scanning the page table, by scanning the physical memory using a private PTE. A detector may allocate a PTE and then perform a loop through all the physical memory available on the system, so that it will just read the separate 4 kilobyte pager, for example, and it will write a dump of memory to disk or something. But the interesting problem here is that Bluepill code is not 4 kilobytes in range. It's much more, probably 16 pages. So it is possible for Bluepill to place its code in separated pages in memory, which do not, which have many. Which will have lots of memory between them. So to that make permutations of the memory. It may just shuffle its code pages in memory, and the detector then should walk the virtual page tables of the host to get the correct correct page table, correct pages of the Bluepill, so that it may apply some memory signatures, for example, to find its code.
Yeah, so that's why we actually can go even more paranoid and actually implement something which is called shadow paging. Shadow paging is what usually virtual machines like VMware, virtual PCs then are using to implement virtualization of physical memory for the guest. Shadow paging, probably most of you know what is it. It's just basically about intercepting CR2 register inside the guest, pointing it to our copy of guest pages, which are GPT guest page tables, to our shadow page tables, and now marking guest pages in such a way that, like, not present, that any access to them by guest will cause an exception that we will catch. And if we catch exception, we actually see what guest was trying to do with its own page tables, and we update our shadow page tables, which actually has the real mapping for the guest virtual to physical memory. There is nothing tricky. No, it's tricky, but it works well, implemented by all the virtual machines, so it's possible to be implemented. The AMD Barcelona, which is coming like next month or something, will bring nested paging, which is a hardware version of shadow page tabling, which makes it much easier for people to actually implement shadow page tabling or nested page tabling. So obviously, we didn't implement shadow page tabling, just shadow paging, just because we don't see detectors doing even that. And we still have like permutation. But still, if we get processor implementing nested paging, that probably would be not that difficult to implement nested paging. For example, that would allow us to defeat Adams' Peel, the Kate-Adams algorithm, as I said before. The lack of IMMU, the lack of a hardware method to prevent DMA devices to do DMA attacks, like reading, still makes it possible for the detector to use one of the I/O devices to read the memory of the hypervisor. But, well, come on, this is pretty crazy. I mean, detector exploiting some device to actually do the DMA read of the memory, to scan the memory, and then, well, decide what is a malicious and non-malicious hypervisor. This is pretty... But still, IMMU is also coming 2008 or something. Okay, nested hypervisor. This is probably the most important part here. Well, first, if Bluepill didn't actually support nested virtualization, then it would be easy for the detector just to try to create a test virtual machine. And if it failed, it would be suspicious. So we need to support nested virtualization. And we do it this way. I showed this slide last year, and I said that we didn't implement it. And in the meantime, we implemented for the new Bluepill. So here's the idea. There's a Bluepill. Bluepill executes VMrun. Here's the guest operating system that we Bluepilled. And now let's say the guest tries to execute a virtual machine that uses VMrun that we intercept. We intercept the VMrun. We realize that guest was trying to create a virtual machine. We look at what VMCB it used, and we execute VMrun on behalf of the guest, however, using VMCB2 prim, which is the union of VMCB2 and VMCB1, if we consider interception, the set of interceptions. And then we execute VM2, which is the nested, which VM1 becomes a nested hypervisor right now. Let's say there is an intercepted VM2. This brings us back to the hypervisor, which realizes that the intercept was from the VM1 guest. So it resumes the guest, emulating that it actually received the intercept. There is a catch here, however, because normally this VM1 hypervisor, emulated hypervisor, expects that the intercept is delivered using VM exit processor exception. However, we deliver it using VM run. We assume the guest and not use VM exit. The problem here is that VM exit is supposed to clear GIF global interrupt flag. So the hypervisor expects that at this point, GIF is 0. There is no interrupt, and the interrupts are buffered until hypervisor executes the STGI instruction which sets GIF to 1. However, we assume the guest using VM run, which does the opposite. It actually sets GIF to 1, which means interrupts are allowed here. However, this does not prevent us to actually run Bluepill inside another Bluepill. So we spent lots of time, like a lot of time, implementing this support for nested Bluepills. And yes, we can run nested Bluepills inside another one. Like yesterday at the training, like 3 people at least successfully ran 20 Bluepills inside each other. They couldn't run more because the system got very slow. And it got slow just because they were using debug outputs using serial cable for debugging. So every debug print was like, it's very, very slow. If we disable debug prints, then the only limit would be the available memory. Just a few weeks before this training, we found out that Virtual PC 2007 is actually a VMM that uses virtual machine, that uses SVM extensions. It can be enabled. And so we tested. It's actually, it's very interesting because if you run the virtual PC or virtual server on your machine, then you see that it loads a hypervisor that is a hypervisor for its guests, like ring -1. However, it's just a kernel module for the rest of the kernel and the rest of the host operating system. It means it's not the hypervisor for the host operating system, which means that you can freely load Bluepill right now. It doesn't prevent you, it doesn't intercept VM run. Even more, it doesn't actually cheat about SVM EBIT. It just sets SVM EBIT in the IFA register. So if we start Virtual PC, it's not surprising that in the host system, the SVM EBIT is set. So actually, if we now loaded Bluepill here, Bluepill would not have to intercept IFA accesses, which means all the methods that we spent half an hour discussing, like TLB profiling, like this Edgar's counterattack, etc., will not work by definition, because read-MSR IFA will not cause VM exit. So we tested our Bluepill, whether it can actually run Virtual PC. That would be the picture. We load Bluepill. So instead of another nested Bluepill, we have nested VPC hypervisor. And it doesn't intercept any SVM IFA, read-MSR IFA. However, okay. Because of this GIF thing, we can run VPC until it runs the guest in a real mode. Works fine. However, if the VPC guest switches to protected mode, then we actually, after a few milliseconds, the VPC crashes. So we trace it down. We spend like a lot of time tracing it down to this GIF problem. And Alex will tell you for the next minute a little bit more about it. Or maybe I'll tell, because we are really running out of time. So what we currently try to do is just to implement, what we implement is currently that if you are here, so until we intercept STGI instruction in the guest, and until actually the guest executes STGI, we actually collect all the interrupts in a buffer. And only when the nested guest executes STGI, we try to inject them. This is where we fail. We still have a problem with ejecting them because we need to use a trampoline to do this, and our trampoline actually somehow crashes. We still believe that we can have VPC running as a nested guest within like coming weeks, which means probably would be like next 2 months or something. You probably noticed that we haven't showed any demos today. This is because we thought it would be best if you just play it with Bluepill by yourself. So if you go to this address, you can download the full source code of our current, the new Bluepill implementation, which supports nested hypervisors. You can also download some SVM detectors from them, play with them, and you can also find this presentation there. Just one clarification. This all is not because virtualization technology is guilty. Just because you have virtualization technology doesn't make you more vulnerable. It's not about that. It's not a bug. I'm not exploiting any bug. Some people will say like Bluepill is a bug. It's not a bug. It's just a design problem. The three messages that you want to stress today: we believe that general purpose operating systems cannot have effective kernel protection if they are based on microkernel architecture, even if we have some driver signing thing there. SVM detection is not equal to Bluepill detection. See, for example, this virtual PC, see this problem. And we expect that we will see this more and more often in the coming year, next 2 years. So please make this distinction. Even though most of the SVM detection approaches can be defeated, we still don't know how to defeat the counter detection, though, which is a pity. That's not really that relevant. Bluepill can hide itself in memory using various approaches. Shadow page tagging would be the nested paging would be the most complete, but it's still not implemented. Some references. Thank you very much.